Excellent. Thank you, Catherine, for recording this. So I'm going to spend a little bit of time right now, probably 3 slides, going for those who are not super familiar with scattering and just explaining the experiments. So those of you who are experienced, this will be review. Bear with me though, it's only a couple slides. And again, through our setup, we had a questionnaire, and there's not a ton of super newbies out there, but there are some. So this is the setup of experiments. We put 20 to 30 microliters in front of a solution that's about, well, let's see, it's about 6 microliters of beam profile, or maybe actually 2 microliters of beam profile. But because of dead volume and stuff, we usually put 20 microliters. It's just hard to handle 2 microliters. So we put that in front of an X-ray beam. We have a flight path. This is actually moved to 2 meters at this point. And the X-ray beam scatters X-rays as a function intensity versus angle, okay? And we'll always measure SAXS as a difference experiment, the buffer sample. So this is an image of scattering from the buffer, an image of the scattering from the sample. And this is a completely symmetric profile. So if I draw a line going from the center to the edge in one direction, that data should be equivalent from the center to the edge of another direction. The reason that we collect the entire thing is that you obviously get better averaged signal to noise this way. So you're collecting a lot more photons. But because this is equivalent and that's equivalent, you can convert this into an integrated one-dimensional profile, which is shown here. So what you have is your buffer sample in black and your sample with protein in it in red. And we're interested in the difference, which is the green profile. So X-ray intensity versus angle. And there's an X-ray wavelength component in here. So no matter what wavelength you collect at, this profile should look the same. So a lot of times you get, reviewers asking what was the wavelength, etc. This Q really takes care of that, right? This plots it out. So scattering angle versus X-ray intensity, and this lambda here. And this looks very similar to, Bragg's law, right? So that's where it comes from. This is a very steeply decaying function. So if you have a folded protein, it's going to decay as Q to the -4. So it's going to decay fast. And so we often plot this as on a log scale. And sometimes you'll see a log scale where you're looking at the super small angles. But that's what the same plots look like: buffer, sample, difference. And you can see that the difference between buffer and sample is very small in the high angles, the high Q values. And so you get very noisy data there. Want to also point out that the places where you get the noisiest data are in the high angles, as shown, but also in the smallest Q here. You have a very bright beam background. So this isn't just sample, right? You see it in buffer and sample, this very dark spot in the center. And that's because the X-rays aren't perfectly collimated, or it's not just a laser beam, but you can think of it as a laser beam with sort of a flashlight behind it. And so that's the dark spots, the flashlight, let's say. Because there's so few pixels dedicated to this region, and the intensities are very sensitive in this region, you can get some noise in the small Q, okay? By conducting a pretty straightforward Fourier transform, I mean, mathematically straightforward, but because we truncate at high Q, we don't go to infinity, which a Fourier transform requires. There's some complications to this Fourier transform, but you can Fourier transform the data and get something that is real space distances in angstroms, and sort of the proportion of the population of electrons that are this distance apart, okay? And so this P of R function, this pair distribution function, you can already, if you're know what you're doing, read into it. So DNA has a cross section that's consistent through the whole molecule. So you get a peak at the distance of about 15 angstroms, which is just this yellow bar cross section. For something that's globular, all the distances are pretty similar, so you get a Gaussian shape. And for something that's bilobal, let's say, you get distances that are associated with inter-domain distances, which is sort of represented by a yellow bar, which is this first black peak. And then you've got the inter-domain distances, which is the second peak here. So you can read into that. All right. So what can you expect from SAXS, okay, in terms of information? As I said, your circularly symmetric scattering profile, you have one-dimensional data. Is clearly not going to be enough for you to figure out where every electron is inside your protein. And so people have tried to come up with algorithms to describe how many independent pieces of information there are. And so basically what they've done is they've tried to fit this with a series of sine curves. And depending on how many sine curves you need to fit the data, you say, okay, that's how much information there is. Okay, so that's an estimate of what it is. Of course, there's also a noise component. So let's see in these curves here, there's a perfect scattering profile, with 1% error. Then there's also sort of the noisier data sets. So that also degrades how much information you can extract, let's say, from a curve that's noisy versus straight. So having done this study, Sergin and Panarev et al. Have got this Shannon program, and they can estimate how many unique pieces of information you're going to collect from your SAXS profile. And it's about 40 to 10, depending on the quality of your data and the shape of the molecule and the Q range you collect. Okay, so something like that, 40 to 10 unique pieces of information. And that amount of information, again, not enough to reconstruct a protein structure. They are constraints, okay? And so what you need when you're trying to understand something where you only have 10 to 40 pieces of constraints, it's super helpful to have other pieces of information. So if you have 10 to 40 constraints, and those constraints are about something that looks like a car, you can start trying to connect what you know about the object and these number of constraints, right? So adding information in a priori, like beforehand, and then comparing it to what you've measured with SAXS is super helpful. So you're comparing, pants versus a jacket, you're comparing, human head versus horse head, etc. That is sort of the complementarity that you want, okay, to make. So having a homolog, and obviously I'm heavily hinting, and we'll get into this in a bit, AlphaFold 2 is one of those things that you can start messing with. Some of these constraints you can immediately make connections to with real physical things, right? So the smallest Q area is sort of radius of gyration and mass. The next part's like radius of cross-section, there's volumes and degree of freedom. We have all these fancy tools, right, to help us do that. But some of these other things at the high Q, it's just sort of a combination of structural features that produce this scattering curve, okay? So there's not like really an analog to a one parameter, not generally, right? So it's just sort of all the features from around the molecule contribute in sum to this kind of a scattering curve. All right, so just reiterating that, you got your scattering profile in seconds. You should be able to extract a mass, radius, duration, maximum dimension, pair distribution function. And there's also shape refinement programs that will allow you to get a shape. All of this stuff should be, you could probably do in a 5-minute process altogether. And there are multiple programs with which to do that with. So the most famous of all is the HT-SAXS program, and Dimitri's group at EMBL has a fantastic suite of software. I think Dimitri's retired, and others have taken on the mantle of maintaining these programs. But they have a fantastic suite of tutorials for learning how to run these processes. So Primus, etc., will give you those parameters I mentioned before. Rob Rambo, who was formerly part of our group but has moved on to Diamond, he created this program called Scatter, which duplicates some of these functionalities but has its own flavor and can do some things faster and other things slower and better or worse, etc. So generally what you'll see is all of us using all of these programs in different ways. There's no unified workflow. I just realized that the place where you download scatter, BioISIS, is down, or not just realized, but that is true. So the place where you can download this is sibyls.als.lb.gov, sorry, up here, and there's a scatter there. And then we also have webinars available for the use of this program to extract those features. And then something that's a little bit newer is BioXTAS Raw, which you'll see probably a decent amount of in this tutorial set for the analysis of SEC-SAXS data. All right. So I mentioned to you that it's nice to know what what you're applying your SAXS extracted constraints on. And so, AlphaFold's a very good thing to do that with. So here's, let's say, the target structure. This is the best AlphaFold trimer that was extracted from the sequence. Another academic group, So if you have raised the gyration and raised the cross-section and volume, etc., you can take something that comes out of AlphaFold and compare that to what you've measured in SAXS and make corrections, right? That makes sense. And then, this is the level of prediction. So especially with AlphaFold multimer, this is, ab initio. But right now, AlphaFold multimer has been demonstrated successfully just for these small kind of connections. But maybe if you add SAXS to it, as Scott or Susan may mention later on, you can constrain something bigger than this together. And we have a capacity to run AlphaFold on a system, and Scott may be talking to you about that later. I wanted to mention that AlphaFold has been optimized on the PDB, and the PDB is a set of crystal structures. And as has always been recognized, the crystalline environment is not the solution environment. So we did a blind study in coordination with CASP and found that over half the proteins we studied, the crystal structure did not agree with the solution structure. Okay, and that means that sometimes you have flexibly linked domains that they're and this is a particular sample where the black curve is the measured sample. We did it in 2 pH conditions, and you can see the SAXS curve changes from something that's extended to compact. So there's dynamics that the AlphaFold will not capture per se. There are also domain motions, so just a little tweaking of the protein architecture that will change between them. So these are residuals from the SAXS measured to the SAXS, for the crystalline structure. So these are differences, and then using all the tools we have, how we can refine the residual to be flatter or in better agreement. So anyway, it's a very remarkable number. 50% of the structures we've tested don't agree, crystalline versus AlphaFold model versus solution model. We also know from our studies that over half the structures are multimeric, not monomeric. All right. Again, this is something that Scott may be going into in detail. So what the workflow could be is you take your AlphaFold model, you compare it with Fox to what you've measured. They don't disagree. They don't agree. And then you go through a program called BilboMD, for example, or other programs. And then you get a matchup between the model. And based on this is sort of flexible, and this is an ensemble where there's some flexibility between them and what you measure in solution. All right, so we run 2 techniques. Some of you will be familiar with one and not the other. So I would just quickly say something about both. And the one that most of you are familiar with right now is the SEC based. So basically you take your sample, run it in SEC as it's coming off the column. You're shooting with X-rays, collecting your scattering data. Based on the averaged intensity across the scattering profile, you can get an elution peak, much like you do for UV. And you can trace the raised gyration, which is the blue curve, across the peak and just see how that differs. And because we also have mols attached, you can also measure the mass, and you can see that while the radius of duration across the peak is changing, the mass is constant. So that tells you something about, conformations that might be existing. So this is the sort of workflow, X-rays, SEC, through SEC, you get these profiles, and then you apply your modeling tools. In parallel, there's a moles, UV vis, quells, and a refractive index that you're measuring. We also have other tools like a dynamic light scattering plate reader and an SPR machine, which we're starting to implement into certain workflows. All right, let's see if this movie will play. Doubtful. So this is the high throughput system. So in the high throughput system, what you're seeing is GFP being loaded up on a plate. So we can collect a plate of samples using our high throughput system in about an hour and 20 minutes. So this particular plate with 3 concentrations of GFP, 2, 5, 7, and 10, or 4 concentrations, 2, 5, 7, and 10 mg per mil with different salts. You can set up this salt screen and concentration screen and examine the impact on your protein conformation and condition. Send that to us in about an hour, and to be collected in an hour and 20 minutes. And so this is the system in operation. What you're seeing is a liquid handling robot. The plate sits over here. Samples are being picked up and transferred to where all the light is over there. And this is the sample position here. And you can see the timer going for, just to prove it's hour 20 minutes. There are steps in here for washing. So there's this ethanol bath and a hair dryer. So, it sucks up some ethanol between samples. Here's the sample being loaded in the sample position. You can see the GFP loading. Sometimes you'll see a bar here. That's the X-ray damage that's occurring. As a function of time of exposure. But again, this is just this thing moving in and out of the plate. This is just captured right when it's at the sample. And then, these are the quality of the data that you'll see. GFP has a repulsive component, so you'll see not your standard SAXS curve, but you'll see a structure factor data there. And again, you can imagine that changes as a function of salt, so part of why we're interested in it. Sometimes you'll see what's being measured here is we usually ask for buffer before the sample and after the sample, so you'll see some discrepancies in the high Q. But generally, the system now works pretty well. And good quality data. So data in quantity at quality is what we've been aiming for. So moving on, we do this by making a liquid handling robot carry needles that have an X-ray transparent window. So we just suck up samples and they go into this spot. X-rays get shot through there. And we're really working hard to reduce the volume required. So we have these low volume needles, and I think we're going to move to the low volume needles going forward. And we've tried other designs with other tricky components, which I won't get into. So this is the low volume needle coming in. These are 10 microliter, 6 microliters in the plate, and you'll see the low volume needle come in at some point, hopefully. Let's make sure it played here. Oh, there we go. Coming in right about, for some reason it won't play the whole way. But we can pick up 4 microliters with a 5-fold reduction in volume going forward. That's still quite a bit of sample to do things with. So I think I came up with, a typical drug screen is like 10,000 conditions or so. So you're going to need a bucket load of proteins to kind of do that kind of thing. So we're aiming to reduce how much we need per sample. So look forward to that. Maybe the movie will play now. Looks like no. All right, so for those of you who haven't seen it, John Tainer was asked to be the editor on a methods in enzymology series dedicated to SAXS and SANS. So it was a methods in enzymology 2023, and there's a huge set of papers, methods papers, and we contributed, I think, 4 or 5 into there out of 30 or so. So there's a lot of description of our setup in there. One of them is describing a drug screening approach for looking at this protein called AIF. It's an important drug screen thing, drug candidate for cancer. Obviously, it's apoptosis, so if you can trigger apoptosis in tumor cells, that'd be fantastic. And so one of the triggering signals here is monomer to dimer transition. And so we're looking for small molecules that can trigger that transition between the two. All right, and so the workflow, as I mentioned, 7,000 samples or 10,000 small molecules would be very difficult. It would take more protein than you'd want. So there's some triaging going on. One is in the library that they're using. So they're using a smaller library, handpicked for being liked as a druggable target, small, cell permeable, etc. So there's some criteria there. We're looking for something pretty simple, monomer to dimer transitions. So first thing you want to do is characterize the system by itself and see if you can see that change. This is a big change, monomer dimer. So yeah, we could see that. There are drug pilot screens. So there's a whole bunch of techniques. Microscale thermophoresis was what they were using here to highlight things that were identified as binding the molecule. So that triage samples down to something like 100. And then we did a high throughput production screen and data analysis. And this is, again, in this methods and enzymology paper. If you're considering doing this kind of screening, please check that one out. And so here are sort of the data, for example, monomer and dimer. This is the pre-screening. There's obvious a Krotke change as well. And for those of you who don't know, this is a log scale versus angle. And so one of the tricks to do is multiply the intensity range versus Q, and then you highlight the sort of middle region in a Krotke plot. And other tricks, there's these normalized Krotke plots as well. And these are the molecules in microscale thermophoresis that were identified. And then going through the data, looking at the intensity XU equals 0, which is sort of connected to mass, the radius of gyration, and how sort of a chi-squared version of volatility of ratio, you can pick out the particular small molecules that cause the biggest changes or in this process. So that's an example. Another thing that we're doing is we're labeling proteins and DNA with gold. This is sort of an example, and you can change the size of gold from 14 angstrom diameters to 200 angstroms. You can change your signal. This is on DNA, so looking at the gold to gold distance. So this is 51 base pairs versus 71 base pairs. So you can see that the wiggles, the periodicity of the wiggles in the small q change depending on how long the DNA is with these golds attached. And in Fourier transform, you get this kind of a profile where you get this sort of intra gold distance that's just within, and then the inter gold distance between the two, depending on. And so here, the 51 base pairs has a peak at 250 angstroms apart, and then the 71 base pairs has a peak at 300 angstroms apart. 300 angstroms is a little bit wider just because there's more flexibility in DNA, etc. So these are the kinds of details you can pick out. The best part about it is, and the reason we're doing something that's this complicated, putting gold on, is that you can get up to 10,000 times the signal. So when I was saying you need bucket loads of protein to do the SAXS, with this, you need 1/10,000th of the bucket, right? And so this is a PARP 1, which maybe many of you have heard of as a drug screen. It will bind NICs. And so we're looking at things that either inhibit the recognition of NICs for chemotherapy purposes, or other reasons that we want a tool compound to understand the mechanisms of PARP. And so when we put PARP on a 31 base pair, we see a big change. And there's controls here for non-nick DNA as well. So things stay the same, things are the same, but when it's got the right construct, it will bend the DNA, shrinking the distance between golds. And so with this, we've already also done a large screen of something like 350 compounds, which we're working on the analysis of. And I won't go through the details. So one of the things that many of you struggle with, we do too, is that processing is slow. And so we are working on a library to increase the speed at which we can process data. We've created some of these things which you'll hear about today, ways of analyzing the data sets, depositing the data sets, etc. Yeah, we're working through this, and hopefully we'll finish that up this year. Radiation damage is a problem. As you expose the sample, you remember that bar in the GFP that was appearing, the sample doesn't stay the same. And so we've developed some tools right now run by hand, but hopefully automated in the future. These are all the scattering profiles from GFP starting. The first exposures are on the lower end, and the longest exposures are on the top end, and then sort of averaging them all is this black curve with the lowest noise. But obviously what you really want is the least radiation damage sample, which is somewhere down here. So we have a web tool for helping you evaluate that. And again, there's tutorials available. Didn't mention this, and I meant to. So we have a YouTube channel on our website at sibyls.als.lbl.gov. You hit that webinars, and we go through what scatter can do. We go through this frame slice tool, past workshops, and in fact, this workshop will also get posted on that YouTube channel. So here's, for example, the radiation damage. And this is the radius duration as a function of exposure. And you can see that the radius duration sort of sigmoidally transitions between sort of 17 or 16.8 angstroms, and then suddenly it pops up to 18 angstroms. So you want to keep as many frames as you can before radiation damage takes hold. There are many types of samples. Just because you have a green sample that looks like this is from a lipid nanoparticle, doesn't mean everything's wrong. This is actually just fine. And so you can't use radius duration to determine radiation damage. So we have to create all kinds of processing tools for aggregated, what seem aggregated, for noisy samples, for things that have good behavior, for things that have just sort of a small amount of aggregation, but then have good behavior, etc. So it's taken a while to develop that suite of programs.
Greg,
yeah.
Sorry to interrupt. Just giving you a couple of minutes warning. We're running a bit late.
The last 2 slides.
Great.
Thank you, Catherine. And then there's data with structure factors, for example, and this is because, let's say, a charged GFP does not want to be close to another charged GFP, so it's restricting it far away. So fitting that function, like there's some repulsion going on. So learning how to use that kind of behavior, where no molecules are this close apart, but then suddenly you have a big peak, etc. So creating that. And this is my closing slide. All this effort takes a lot of people, and we really appreciate our user community, and we hope that we can mutually work together to produce a lot of great science. We have, I think, we've averaged about 33 papers per year. Even with the shutdowns that are going on, the sort of 3-month blocks that were cut out. And what we've done to compensate for those small amounts, for the times that we were missing, is we've really increased our throughput. Yeah, so that's how we've remained consistent through the years and hope to continue to do so. All right, that's the end of my section. I would like to hear from you guys a bit. So any questions, any hellos anyone wants to say, any thank yous to Daniel, memories of Daniel? Anyone wants to say? Quiet community.
Greg, I had a question.
Great.
How, you know, the gold labeling is used to be a really tricky business. Is it more robust now? Is it still tricky?
I would say that more people know how to do it for different reasons, and that's the key, right? And if you're looking to us to do it for you, that won't happen. We have published a paper on how to get it done as well, and it's very clearly spelled out.
Great, thank you.
Other questions, concerns? I would really like to hear today about.
Hi, I have a question. Sorry,
Yes.
I'm a new user to SAXS. And I was wondering, because you mentioned that we can look at the binding of DNA with proteins.
Yes.
Will it be possible to look at like protein-protein interaction using SAXS?
Absolutely.
Just like dumping in two samples of, so I don't need them to bind. Okay. And another one is it possible to look at the encapsulation of proteins and RNA?
Encapsulations of proteins and RNA in what?
So the protein is a capsule, and then the RNA supposedly should be encapsulated inside the protein. Yeah.
Yeah. So there's two. You'll see the size exclusion coupled SAXS in a moment. And so if you have a complex, you know, it could be transient, right? That if you mix two proteins together, you'll get the two proteins separate and then a component that's a complex, right? And so the size exclusion, running the size exclusion will allow you to analyze all three of those components at the same time, you know, with one sample. So you'll use the HT-SAXS for that. And your last example, RNA encapsulated by protein, right? So you'll have free RNA maybe because you have excess RNA, and then you'll have protein with RNA encapsulated. So you have these two peaks. You want to separate that because otherwise it's going to be mixed up. And so the HT-SAXS is perfect for that. But let's say that you've figured out a condition where, you know everything's 1-to-1 and are happy, and now you're studying sort of maybe the folding of the RNA inside with different counterions. Then you could use a high-throughput SAXS approach to do a whole bunch of screening. Or maybe what you're wanting to know is under what conditions does most of the RNA get encapsulated? So then you might do a high-throughput SAXS screen. Does that make sense to you, Valerie?
Yes, thank you so much.
Okay. Other questions? All right. Please, if you remember anything or have any questions, please actively participate. Yeah, none of us want to be here for full day and just hear ourselves speak. So please do what you can. All right, I'll switch that over now to, I believe, Dan.